A surface is first exposed to ultraviolet radiation and then to visible light. So ultraviolet to visible. Energy of ultraviolet is more than energy of visible. If energy is more, then stopping potential is also more, isn't it? So how to establish this? E equal to phi plus kinetic energy. Kinetic energy is charge times stopping potential. Therefore, E equal to phi plus EVS. Is same for both the radiations. More for ultraviolet. Yes. More for visible. No. Depends on intensity of incident radiation. No. In a photoelectric effect experiment, the stopping potential for the incident light of wavelength 4000 angstrom is 2V. If the wavelength is changed to 3000 angstrom, the stopping potential will be. Observe 4 options. All these are with respect to 2V. So you don't have to calculate anything. 4000 angstrom to 3000 angstrom means the wavelength decreases. Wavelength decreases means energy increases because E equal to hc by lambda. These two are inversely proportional. Okay. So for 4000, if it is 2V, for 3000 it should be greater than 2V. So more than 2V. Which one of the following is not associated with photoelectric effect? Photoelectric effect is instantaneous. Not affected, not associated, wrong statement. Students, underline such words, not, false, wrong statement. Okay, because often we search for correct option and here wrong statement is asked. Photoelectric effect is instantaneous. Statement is correct. This is one of the properties of photoelectric effect. Therefore, we don't want. Photoelectric current depends on frequency. No, because photoelectric current depends on intensity. So we got the wrong statement. So this should be correct. Velocity of photoelectrons depends upon frequency of incident light. Yes, if frequency increases, kinetic energy increases, velocity increases, stopping potential increases. Below threshold frequency, no emission. Yes, true, because if frequency of incident radiation is less than threshold frequency, then there is no emission. Statement is correct. So second is wrong statement. That is the answer for this question. Ultraviolet light of wavelength 350 nanometer and intensity 1 watt per meter square is directed on a potassium surface. What will be the maximum kinetic energy of photoelectrons? 350 nanometer means energy is about 3.5 eV. Let us see. Work function is 2.2. Work function is 2.2. Therefore, kinetic energy should be difference of these two. It's about 1.3 eV. Recall, for violet 400 nanometer, energy is 3 eV. If this wavelength is reduced to 350 nanometer, then this energy should increase. So let us increase this slightly. You can increase this to 3.4 eV, doesn't matter. If energy is 3.4, work function is 2.2, so difference of these two is 1.2 eV. 1.2 means closer is 1.3, so 1.3. What is the use of intensity means? Intensity doesn't affect the kinetic energy. Therefore, we don't have to consider this value. In a photoelectric effect experiment, photoelectrons are emitted from a surface when exposed to certain radiation. the applied voltage is increased, then the maximum kinetic energy of photoelectrons emitted remains same. Applied voltage affects current, isn't it? So from this standard graph, we know that voltage affects only current. It doesn't affect maximum kinetic energy. Therefore, it remains same. If in a photoelectric cell, the wavelength of incident is changed from 4000 angstrom to 3000 angstrom, then change in stopping potential will be change in stopping potential. Okay. Again, distinct values. So it should be easy to solve. Energy is phi plus kinetic energy. Kinetic energy has stopping potential EV. This is phi. Energy is given in terms of wavelengths. So hc by lambda. So for one wavelength, if it is V, means for 4000 angstrom. 4000 angstrom, it is hc by 4 10 power minus 7 equal to 5 plus EV1. For 3000 angstrom, hc by 3 10 power minus 7 equal to 5 plus EV2. This is greater than this because denominator is less. Therefore, this minus this. This minus this, phi get cancels, 0. This minus this, E is common factor, V2 minus V1. This minus this. Take common factor, hc by 10 power minus 7, 1 by 3 minus 1 by 4. This is change in potential, delta V. Hc. H is 6.6 10 power minus 34. C is 3 10 power 8. 10 power minus 7. Charge of electron, take it to the other side. 1.6 10 power minus 19. 1 by 3 minus 1 by 4. 4 here, 3 here. 4 minus 3, 1. 4 into 3, 12. Observe carefully. 1.6 one time. This is approximately 4 times. 4, 3, 12. 4, 3, 12. 12 is here. So manage 10 power. It turns out to be 1. So delta V is equal to 1 EV. This is delta V is 1 volt potential, right? Therefore volt, 1.03 volt. You can also say for 4000 angstrom it is 3 EV. For 3000 angstrom it's approximately 4 EV. So difference of these two is 1 EV. That is also possible. Okay. Difference is 1 EV, so corresponding potential difference is 1 volt. In a photoelectric effect experiment, stopping potential is 1.9, energy of incident is 3.4. Work function of the photosensitive material is nearly 3.4 minus 1.9 is how means energy of incident. E equal to work function plus kinetic energy. Kinetic energy is charge times stopping potential. This is 3.4. Work function is 5. Charge times stopping potential 1.9. 1.9. So difference of these two is 5. 0.1, 1.1, 1.5. 1.5 EV. 1.5 EV in terms of joule. So 1.5 into 1.6 10 power minus 19. So 1.6 into 1.5 is 2.4, 10 power minus 19. In a photoelectric effect experiment, stopping potential is 1.4. Energy of incident is 4.5. Threshold wavelength of photosensitive material is about. Incident is 4.5. This is 1.4 eV, kinetic energy. Difference of these two is 3.1 eV. 3.1 eV is for violet, which is about 400 nanometer. Therefore, 4000 angstrom. If you don't get it, let me explain a little bit. Energy equal to work function plus kinetic energy. Energy is 4.5. Work function. Kinetic energy, potential is 1.4. Therefore, this is 1.4 eV. Difference of these two is 5, which is 3.1 eV, which is 3.1 into 1.6 10 power minus 19, and 5 is hc by lambda naught. So lambda naught is, take this to this side, bring these numbers to denominator, 3.1, 1.6 10 power minus 19, h is 6.6 minus 34, c is 310 power 8. This 4 times. This one, approximately this one, equal to 10 power minus 34, 10 power 8, minus 19. Minus 19 goes to numerator, minus 27. 27, this is 10 power minus 7. So 4 10 power minus 7 is 4000, 10 power minus 3, 10 power minus 7. See, I included 3 zeros to compensate that 10 power minus 3. 10 power minus 7 is already here. Therefore, 4000 angstrom. When light of wavelength 300 nanometer falls on a photoelectric emitter, photoelectrons are liberated. For another emit, light of wavelength 600 nanometer is sufficient for liberating photoelectrons. Ratio of the work functions. Work function is hc by lambda naught. These two are inversely proportional. Threshold wavelength and work function. Students, if they are inversely proportional, okay, then in this statement you will get these two values. If they are inversely proportional, then take these two in the reverse order. So 600 nano by 300 nano, which is 2:1. 2:1. If the quantities are directly proportional, divide this by this. Inversely proportional, this by this. When light of wave number falls on a photoemitter, photoelectrons are liberated. For another emitter, light of wave number per meter is sufficient for liberating photoelectrons. Ratio of work function of the two emitters is, so work function is hc by lambda naught. hc, 1 by lambda naught is, 1 by lambda is wave number, okay. Lambda naught is nu bar naught. These two are directly proportional because in the problem in terms of wave number is given. Since these two are directly proportional, this by this number appears first in the statement. This by this is 0.5 by 0.25, which is equal to 2:1. So 2:1. Which of the following graphs represents the variation of maximum kinetic energy of emitted electrons with frequency nu? Maximum kinetic energy with frequency, it's a standard graph. Frequency, independent variable, maximum kinetic energy dependent variable. What else we get from this graph? Slope gives Planck's constant, x-axis threshold frequency, and y-intercept gives work function. When a piece of metal is illuminated by monochromatic light of wavelength lambda, stopping potential is 3V. When same surface is illuminated by 2 lambda, stopping potential is V. E equal to work function plus kinetic energy. In terms of wavelength, so it is hc by lambda equal to phi plus kinetic energy in terms of stopping potential. So EV. For lambda, hc by lambda equal to phi plus 3V. So E3V. And for 2 lambda, hc by 2 lambda equal to phi plus V. EV. The value of threshold wavelength for the photoelectric emission. Threshold wavelength is there with phi, isn't it? So we have two equations. I need to retain phi, so I don't want this. There is 3, so multiply throughout by 3. 3, 3, 3. Now observe, this minus this 0 plus this minus this 2 phi. This minus this 3 by 2 minus 1 is 1 by 2. Hc by lambda. And what is phi? Hc by lambda naught threshold wavelength, and it is hc by 2 lambda. Hc get cancels. This implies that lambda naught, which is threshold wavelength, equal to 4 lambda. When light of wavelength lambda is incident on the photosensitive surface, the stopping potential is V. When light of wavelength 3 lambda is incident, stopping potential becomes V by 6. Just like previous problem, take the equation E equal to work function plus kinetic energy. E in terms of wavelength, hc by lambda equal to phi plus kinetic energy is EV. For lambda, for 3 lambda, equation becomes hc by 3 lambda equal to phi plus V, EV. Oh, for lambda it is V. For 3 lambda it is V by 6. V by 6. For lambda it is V. hc by lambda equal to phi plus EV. So this threshold wavelength is with phi. Phi is hc by lambda naught. I need to retain phi. Here there is 6. So let me multiply throughout this by 6. 6 because coefficient of EV is 1. 6 by 6 is 1. So multiply throughout by 6 into 6. This becomes 6. This is 6. This minus this 0. This minus this 5, 5. 3, 6, 2. 2 times 1 time. So it is hc by lambda. But what is phi? Phi is hc by lambda naught into phi. This is hc by lambda. This implies that hc lambda naught equal to 5 lambda. 5 lambda. For a certain metal, incident frequency nu is 5 times the threshold frequency nu naught, and maximum velocity is 8 10 power 6. If nu is 2 nu naught, the maximum velocity of photoelectrons. So frequency, velocity. E equal to work function plus kinetic energy. This in terms of frequency is h nu, phi plus kinetic energy in terms of velocity half m v square. So you can understand that we have to play with two simultaneous equations. So with frequency nu, which is 5 times the threshold frequency, nu is 5 times h 5 nu naught equal to, since it is given in terms of threshold frequency, let us write work function in terms of threshold frequency plus half m v square. So this becomes 5 minus 1, 4 h nu naught equal to half m. Velocity is 8 10 power 6, 8 10 power 6 square. Next, if frequency is 2 nu naught, so let me substitute for this equation where frequency equal to 2 nu naught. So h 2 nu naught equal to phi is h nu naught plus half m v square. So this gives 2 times 1 time, take this to this side, h nu naught equal to half m v square. Now this is equation 1, right? Bring it here. 4 h nu naught equal to half m 8 10 power 6 square. Divide. This equation 1 is this equation. This is equation 2. This is equation 2. h nu, half m, half m. Look at these beautiful numbers. They rearrange themselves. V square 4 something square. This implies that take square root 2 times v, 2v equal to this side with square root. It is simply 8 10 power 6, or v equal to 2 4 2 8 4 10 power 6 meter per second, 4 10 power 6. Such calculations becomes fast once you practice. So you are thorough with simultaneous equations. Solving with simultaneous equations means it is very easy. In 10th standard also you have solved such problems in math, isn't it? Equations with two variables. In photoelectric effect, which of the following is correct? So we have to check all of them. Stopping potential depends on the frequency of incident radiation. Yes, this is correct. E equal to work function plus kinetic energy. Kinetic energy has stopping potential. Phi has threshold frequency, threshold wavelength. E has frequency and wavelength. Okay. So this is dependent on both E and phi. So stopping potential depends on frequency of incident radiation. Photoelectric current doesn't depend on applied potential. Statement is wrong, because in this graph we have seen that potential affects the current. Maximum kinetic energy of photoelectrons depends on intensity of incident light. No. In this graph we have seen that intensity affects current. Intensity affects current, but not kinetic energy. Maximum velocity of photoelectrons depends on number of incident photons. Number of incident photons means intensity, isn't it? Recall, intensity is energy by time by area. Energy is number of photons energy of each photon by time area. So intensity is proportional to number of photons. Number of photons affects the photoelectric current. So this statement is wrong. Students, when you get question like this, where nothing is mentioned in the question, just check the right statement, check the wrong statement or incorrect statement, then you have to check all the 4 options. Okay. If in the examination you are running out of time, means that time if you get the answer, stop checking others. But when you have time, please go through all the statements and analyze. And during practice session, make sure that you go through all the points and understand. The threshold wavelength for a photosensitive material is 5000 angstrom. Photo emission occurs. Threshold is 5000 angstrom. So photo emission is possible only with lambda is less than lambda naught. Wavelength greater than 5000. No. Wavelength less than 4000. Wavelength less than 5000 is same as wavelength less than 4000, isn't it? So energy is sufficient to remove electrons. So wavelength greater than 6000. 5000 wavelength, 5000 angstrom wavelength cannot remove electrons. Certainly 6000 also cannot remove, because energy is inversely proportional to wavelength. If wavelength increases, then energy of incident photon decreases. So even with 6000 angstrom not possible, or greater than 6000 angstrom not possible. For any wavelength, provided light is incident long enough. Light is incident long enough means that doesn't increase energy of each and every photon. So this is wrong. Quantum theory says with longer time, more energy cannot be supplied. The photoelectric threshold of a metal is nu naught, when light of frequency 3 nu naught is incident on it. The maximum kinetic energy of emitted electrons is 2 h nu naught, isn't it? So E is 5 plus kinetic energy in terms of frequency. So this is threshold frequency h nu naught. This is frequency of incident h nu, and this h nu is 3 nu naught. So this is h nu naught plus kinetic energy. So 3 times 1 time is 2 times 2 h nu naught equal to kinetic energy 2 h nu naught. When visible radiation is incident on the surface, no photoemission takes place. When a different radiation is incident, photoelectrons are emitted. The radiation is most likely electromagnetic spectrum, visible, wavelength longer than visible, IR, shorter, UV. So in this direction, wavelength decreases, increases. If wavelength increases means energy decreases. If visible energy is not sufficient, certainly higher energy radiation should be used. Higher energy radiation means ultraviolet. So that is why if visible cannot remove electrons, then ultraviolet should be able to remove. IR is not the answer, because IR energy is, this energy is, energy of IR photon is less than energy of visible. So with much lower energy, it is not possible to remove electrons. Something like this. This biscuit packet costs 12 rupee. You are giving 10 rupee to the shopkeeper. For 10 rupee you can't get. So which is the next denomination where you can get means, next denomination it should be 20 rupee, isn't it? Or else 10 rupee plus 5 rupee, 15 rupee, then you can get this. means we have to go to higher than 10 rupee. So that is the meaning. If visible radiation cannot remove, then ultraviolet should be used to remove. A photon is incident having frequency 10 power 14 per second. Threshold frequency is 5 10 power 13 per second. The kinetic energy of the ejected electrons, E equal to 5 plus kinetic energy. In terms of frequency, h nu equal to h nu naught plus kinetic energy. So frequency, incident frequency is 10 power 14. So h 10 power 14 equal to h threshold frequency is 5 10 power 13. 5 10 power 13 is 0.5 10 power 14. So this is 0.5 10 power 14 plus kinetic energy. This is 1 time, this is 0.5 time. Take this to the other side, we get 0.5 10 to the power of 14 h equal to kinetic energy. Now this kinetic energy is in joule, so we have to solve. 0.5 10 power 14, h is 6.6 10 to the power of minus 34. So half of 6.6 is 3.3 10 power. This is minus 20. So kinetic energy is 3.3 10 to the power of minus 20. 3.3 10 to the power of minus 20. So there are two. 3.3 10 power minus 21 minus 20. When a certain metal surface is illuminated with light of frequency nu, the stopping potential for photoelectric current is V0. Nu stopping potential is V0. When the same surface is illuminated by light of frequency nu by 2, stopping potential becomes V0 by 4. The threshold frequency of photoelectric emission, E equal to 5 plus kinetic energy. Now let us write this in terms of frequencies. h nu naught plus kinetic energy. Frequency nu, stopping potential V0. So h nu equal to h nu naught plus E V0. When the same surface is illuminated by light of frequency nu by 2. Now frequency by 2. Nu by 2, this is h nu naught plus stopping potential becomes V0 by 4. E V0 by 4. The threshold frequency for photoelectric emission. Threshold frequency is here. Simultaneous equations. We don't want this term. So multiply through this by 4 or divide through this by 4. So let me multiply 4, 4, 4. 4 by 4 is 1. This minus this 0. 4 times 1 time 3 h nu naught. 2 1, this is 2. This minus this 2 times 1 time, so h nu. Therefore threshold frequency equal to nu by 3. Nu by 3.